Hello again. Welcome back to my stream. It's Friday, so we're going to do some hacking work, hacking practice. As promised on the last hacking stream, I have continued to do research into how angr works and have taken a stab at one of these intro sort of challenges that are explicitly built for being a introduction to how to use angr to solve I guess essentially crack me's, and it looks like maybe eventually pwntables. That part I'm particularly interested in because I think my thinking on it was how to or my thinking on it was that you would use it for crack me's and other challenges that are essentially just reversing rather than exploits. Granted, I don't think it will generate an exploit for you, but I suppose you can use it to uncover a condition which would be exploitable. So uncover a scenario in which a buffer overflow could happen, or maybe a heap overflow, something of that nature. So I think we will see that if we continue through a number of these challenges. So looking at the stream that we have right now, or rather the screen that we have visible now, you can see the angr CTF repository, and it's got several different challenges. I've just gone through this one to sort of verify that I have even a baseline understanding of angr well enough to be able to use it, and so that I can do something interesting on stream. And the actual angr documentation going through the core concepts was definitely enough to be very to understand perfectly what's going on with this first challenge. And the names of the challenges, at least these first three, are sort of names of not exactly features, but like mechanics that you might use in terms of how you would apply the features of angr. And so I assume the second one is going to be showing how to make use of this other feature. So I went ahead and reset my work on the first one so that I can show the process on stream. And what is going on with that? Okay. So right now we just got that one first binary in here. And we can, let's go through the standard process that we were doing with all of the previous ponables in the Nightmare course. We look at it in file, we see it's a 32-bit elf. It is dynamically linked, it's not stripped. And check sec. I don't have, because I'm in the virtual env. Do I want to bother? I suppose we will not bother with, I can do it over here. Or not. I'm not in the VN here. Weird. It's probably because I installed angr globally as well, and maybe that interferes. Let's see if I can reinstall Pwn, or Pwn tools rather. Let's do install 6. Is there like a force install? Force reinstall. They're only going to do Pwn tools. No, it's doing all of them. Okay. So outside of the VM, I'm going to force reinstall Pwn tools. Hopefully that will fix whatever the issue was. No, cannot uninstall PySerial. Oh, great. Well, shit. Have I... Well, I don't know. That part is working again, but I feel less confident that my Pwn tools install is going to be working from here on out. So according to Pwn tools checksec, we've got Canary, we've got NX enabled, and then no PIE. So, you know, we could attempt a ROP attack on this if this were a pwnable. It is not a pwnable, at least not how we're using it. It's more in the crack me variety. So if I run it and I want to enter a password, we can try test, and it says try again. Okay, so let's open it up in Radar. And we see there is the main function. So if we look at it in Radar, we prompt for the password, we scan in whatever is referenced here. Seven 5 8753, which is %8s. So it takes up to 8 characters, I guess. And then we loop through 8 times, going through and calling this complex function. And you can see it does some stuff here. My guess is this is a optimized division. It has that feel, let's say. It's more of an intuition-based assessment. But you've got a certain large number that is a constant. Then you do a mul, a shift right. Is that shift right or? Yeah. It's just, okay, so it's like assigned shift right versus the SHR for unsigned. Okay. And then, yeah, you maybe do multiple shift rights and stuff. So it feels like that, but I don't know for sure. Oh, and maybe if it's not long enough. Why are we comparing against 0x40? What is arg8? EAX is so if the first character is less than 40, then we get try again. Okay. Basically, if it's not an alphabetic character, I guess, then it doesn't even bother. Granted, that's also not the password, so I don't know if we're getting the try again from down here or the one from inside complex function, but it doesn't matter. The point is not to fully understand this algorithm right now. We could, if this were just a very early category crack me, and I wasn't thinking to use angr and apply its tool set, I would look through this and go, well, we're doing a string compare against this string, so let's give that a shot. So we run it, we provide that. Well, that's not the string. That's not the actual password. So it must be that it's taking our input, modifying it in some way through this loop and calling complex function, and after all of the modifications, we can get it to equal that string. But how do we figure out what the initial value needs to be such that all of those modifications result in this exact string? Because that's really, we could use GDB and go and cheat and force the value in right before the string compare, then we would get it to print good job, but that's not actually resolving anything. That's, as I said, kind of cheating as far as this kind of program is concerned. So what we can do is use the program angr to analyze this, and it effectively will emulate the behavior in such a way that it's able to, when it gets to the string compare, it is able to create a graph of all of the mathematical relationships that are involved in both the comparison logic and all of the modifications that happened in this loop. And it can then sort of analyze and assess that graph of relationships and figure out which initial inputs through the constraints that are set by going through this will result in going down this path to the good job output. And that's exactly what we're going to do. So it's building a lot of data about the potential ways that this program could work, and going backwards from this endpoint that we assign, where we want the program to end up down here. We If we want it to end up down there, then it goes backwards through all of its graph of possible inputs and figures out, okay, here's at least one of the inputs that would work for it. There might be multiple inputs that could result in this string being generated so that the string compare passes. But we only need one of them, so we can find that by using the angr program, and this repo has helpfully provided us with a scaffold Python script, which I'm actually going to delete the comments. I did read them before, but it's going to make it a bit clearer if we take these out. So first we need to tell it what binary we're working with, and I'm going to say, as it had suggested, let's just put argv1 so we can pass the name of the binary as an argument on the command line. And then it's going to create a project out of that and generate, and then we ask the project to generate for us an initial state, which is defined as the entry state, so the state of the program when it is going to start running the main function. And this will allow us to do that emulation that I talked about, starting at the first instruction in main, at this LEA instruction, I guess. Okay, and then we generate a sim manager, which is just sort of a tool for managing one or more states and telling them how to progress through the emulation process and be able to check the results and do all kinds of fancy stuff. And we need to give it an address that represents when a condition that we want to happen does happen. In this case, it's getting to this particular basic block. So that's our win condition, basically. The one that we are going to find is the condition where we get to this address, because that means that whatever we had input was correct. So I'll put in that address, 804.867.5. Yeah, 8675. Okay. And then we run the simulation manager and say explore all the possible paths through this program, looking for a path or a state and like successive resulting states in the execution path that ends up getting us to this address with the instruction pointer. Basically, if the instruction pointer register ends up at this address at some point, that's the path or set of paths that we're interested in. And actually, the explore just stops when it finds the first one that meets that condition. Okay, and then what it does is it puts the state object that represents that execution path. It puts that in a category which they term as a stash, puts it in a category known as found. And so if found has more than 0 states inside of it, because it's a list, so if it's not an empty list, then we come into this if statement and we find the state that was the first one in that list. So solution state is now the state object that is the first one that we found that hit the good address. And it, as a state, it actually can retain its whole history of how it got to where it is, It doesn't have to track that. You can sort of customize it and say, track which basic blocks you went to, track which functions that got called, or track the current call stack, basically. You can track every instruction that got hit and like what all the memory modifications were as well, if you really need to get full details on it. But one of the nice things for our purposes is that it will track the input and output data specifically for standard in, standard out file numbers. File descriptors. I don't know if it can track arbitrary ones if it opens a file or something. I would presume that it can, but all the examples I've seen so far are just like you can provide it data that it would use for standard in. You could, or in this case, we didn't provide it data. Roger Turnwood presents. Thank you for following. So we didn't actually provide it any input data because we don't know what it is. That's what we're searching for, basically. But as it simulates the state, it will essentially take guesses as to what that input data needed to be in order for the condition to eventually arrive at the good output. And it minimizes the number of possible guesses from quintillions and I don't know, like billions of quintillions of billions, whatever, giant numbers of possible inputs, down to a much more reasonable number of possible inputs because it does a backward sort of analysis on how all of the data relates to each other through the instructions that are actually in the program. So it's going to keep track of what the standard in data was for the state that actually worked. And what we're doing here is we're just saying, okay, now go ahead and print us what that standard input data was, so we can see what it came up with. Otherwise, I guess we would get to a point where it didn't find a solution. Now, it shouldn't get here because this is a example that's been crafted specifically for, being an introduction that works. And I've done it myself earlier, so I have perfect confidence that this will work. The only problem was we need to switch this to Python 3 syntax. So, okay, so that's what it's going to do. And it's going to take a few seconds to do its thing. But then we will get whatever that magic input is that works for this program. And there we go. It actually didn't take very long, I think, because I ran it before and maybe it's warmed up a little bit. But if we go ahead and run the program and pass that in now, we can verify that that results in the good job response. So we got something out of it. And, conceptually, we can compare this against maybe fuzzing, where you would be brute forcing. Fuzzing is like brute forcing a password in the sense of like cracking passwords. You're just going to try as many possible combinations as you can, and the whole way of making that approach viable or meaningful is try as many things as possible. Make that fuzzing, brute forcing approach as fast as possible. So if you look at like this other guy on Twitch, Gamozo, he writes some incredibly highly optimized fuzzing software that basically cuts out the whole operating system and really like shaves off every possible thing that would slow down the fuzzing process in order to get millions and millions of fuzz test cases per second. And you could apply that approach to this program as well. And basically, since we know that it's only 8 characters, and we know that it is going to be a letter, I guess. I mean, it could be anything in the ASCII range above 64. Just because that's what it seems to be like. Oh, it has to be between 64 and 5A. So, which is what? Yeah. So it's actually strictly limited to uppercase letters. So if we do 26 to the power of 8, I think is the number of combinations, or is it yeah, because factorial would be if we couldn't repeat them, I think. And that is what? 208 billion possible combinations, right? So we could use a fuzzing approach, in which case, because this program is really just enter a password, it's pretty much exactly equivalent to cracking a password, except the nice thing with password cracking is if you get a huge dump of passwords, you are amortizing your cost across all of the passwords that you're attempting to crack, rather than, you don't get any major benefit if you're trying to crack a single password, which is what's going on with this program. So if you did that and you were just trying to crack a password, maybe you could get some millions per second, right? It's still going to take longer than this program took, even in the most highly optimized form of trying every single possible thing. Granted, you've got like a halfway chance of getting it right, I guess. So it's half of whatever the maximum time would take. But yeah, this approach is, instead of just trying to be as quick as possible at checking every possibility, it tries to be very smart about eliminating as many possibilities as possible until you have narrowed it down as far as you can, and then you start to maybe do the brute force search through everything kind of approach. I'm always surprised at how quick this kind of thing works. Like, I use Z3, which is a fundamental underlying component of angr. I used it manually at one point, and I had converted a bunch of assembly code into Z3 code effectively, and was like, okay, now I'm going to run it, and I'm expecting, I guess I'll wait a couple hours or something, but it took like 30 seconds. I was highly impressed at how quickly it was able to churn through all of that stuff, because I think this is on the low end of, combination like state space searching. If this were 27 characters, it's going to be far too much to brute force, but it might actually not take that much longer for angr to do it, because it's still able to minimize what it's looking at. Okay, so enough of my talking and sort of trying to halfway describe angr. I'm going to start working on the next one. And so this one I have not looked at all. And this one, they have a lot fewer comments to describe everything that's going on. We can, again, throw argv1 in for the name of the binary. It's going to get us a entry state that is, or an initial state that is the entry point of the program. And then we do the same thing. We get the simulation manager. So now the comment says, explore the binary, but this time, instead of only looking for a state that reaches the print good address, also find a state that does not reach will not succeed address. The binary is pretty large. To save you some time, everything you will need to look at is near the beginning of the address space. Okay. Well, let's look at it in radar. It is pretty large if it's taking this long for radar, even on the first. Oh, I didn't go through all the stuff. File. So it's a 32-bit ELF again. It's dynamically linked. Just to libc and geez, yeah. How big is it? 568K. I guess that's pretty big given that it's dynamically linked, but it's not so big that I would think that radar would have this much trouble, basically. What is going on? Okay. Then, wait, did it not? Okay, now it's killed. Well, we can definitely go to entry 0. Oh, I guess we were already there. Okay. Then let's go to yes. Let's define the function. It's still going, I guess. Jesus Christ. I see. Okay, so this might require us to use something like objdump. Because the problem is radar wants to do a lot of analysis and come up with a control flow graph and stuff. And my guess is that this this binary has been generated in such a way that it just is kind of overkill for a tool that wants to do that. So how do we use it to just print main? Ooh, interesting. Why do I... What the fuck? Something is broken with my mouse-based control. Can we limit the disassembly to a particular function? And We want, yeah, ooh. Okay. Right, this is all part of the main function. So, just an absurd number of instructions, right? That's fine. Then we want we have a call to puts. We have another call to printf, which is, that's the first call. And the only call? Print message. Interesting. And there's an avoid me function. Okay, so what are we doing with print message? I guess we can put the pointer there, or the like good on there, but we get to maybe good, which is after all of this nonsense, and it calls avoid me. Okay, so I think what I'm going to do is consider if we get to print message, that'll be the good case, and if we get to the avoid me function, that'll be the bad case. We'll give that a shot. So print good address is going to be 804.852b, and then avoid me is going to be 804.85a8. Okay, so now when we explore, we are finding things that get to the print message function and do not get to the avoid me function. And fix up the print call, and we'll see if that works. Couldn't find it. Okay, so maybe print message is not the one to use. Maybe we'll look at maybe good. 485b5. Okay, so just to double check, right, that works, or doesn't work rather, and then this one also doesn't work. Interesting. So it found an input that didn't hit avoid, but did get to the maybe good function, but like but didn't find anything that got to print message, which makes sense because I didn't see any calls to print message. Maybe there is a particular situation of calling maybe good. There's a lot of calls to maybe good. And without being able to see any sort of control flow graph on this, right, we need to find which condition is going to print. Well, I can go ahead and find the strings. Right, we want capital D. Not being able to see my cursor is really killing this. Still can't see it. Okay. And obj dump minus D. Can you see this? Okay. Do we get to see strings? There we go. Got RO data. I don't really want it. Actually, that's the wrong. Yeah. We want to. Can I just say obj dump j RO data? Why did it have -j in the man page? Right here. What is that about? Okay. Oh, did I not give? Still doesn't. Okay. We can't do. Yeah, we need to give one of these. Just wanted to show me the string value at the address that is referenced. Let's see. We can do prop gadget. And okay, so that's at 804 80D461E. Okay, so there is a bit of code. Let's see where we're at. Okay, so I put inputs and I didn't find it. Whatever. Okay, so this is our bit where we print out the good jobs thing. So I'm gonna go ahead and call this the success address. For 85E0. And hopefully now whatever input it finds is going to be good. Okay, so as we can get to have a better sense of how it is searching through stuff. It found a path that managed to avoid the avoid me function, and hit at least one of the good, what is it called? Maybe good functions. And we notice they both start with HU. So maybe like starting with HU is necessary to avoid the avoid me function, but then it sort of diverges. Just double check that worked. And so it does have this sort of like searching through all the possibilities. Knight and CTF, thank you for following. Hope you're enjoying the stream if you're still in here. And yeah, okay, so that one was a little bit annoying to figure out what the success condition is. You know, angr is not necessarily the tool to be able to look at a binary and figure out where is the point that you want the program to get to. It's the one that can work out how to get to that point. But if you got to rely on other tools, something like radar, it has its limits as well. And if you have a function that's got 10,000 instructions in it, especially if there's tons and tons of like jumps between them, it's probably gonna die just trying to generate the graph and do all the analysis on that function. So got to keep that in mind, I guess. All right, we'll keep moving on. And we'll get the second one. And let's look at that. Okay, so this one is, what do we name this file? It was find condition. Okay, so it's very useful to be able to search for a state that reaches a certain instruction. However, which is what we've been doing. However, in some cases, you may not know the address of the specific instruction you want to reach, or perhaps there is no single instruction goal. Okay. In this challenge, you don't know which instruction grants you success. Instead, you just know that you want to find a state where the binary prints good job. angr is powerful in that it allows you to search for a state that meets an arbitrary condition that you specify in Python. Using a predicate you define as a function that takes a state and returns true if you have found what you were looking for and false otherwise. Yeah. So what we're basically doing is every step through the simulation, which I think does a single instruction, like emulates a single instruction, but I don't know, could be more than that. I guess could be less than that potentially. I'm not sure. But it is going to run a little bit of emulation and then give us back the new version of the state, which we can analyze through whatever logic we want to write in Python to determine, is this a condition that we were looking for, in which case it'll consider it found, basically. So we need to work out what is the situation that we can analyze for any given state, which tells us that we have printed good job. So this makes perfect sense. Right now, our is successful function, which is the one that's going to check whether or not the state has reached the point where it considers the password successful. It's got a bit of code that they provided us where we basically get standard output. Whatever has been printed to standard out, we get that as a string. And and we can say something like, and I think we get it as a bytes string based on the examples that I saw on the angr website, since this is now Python 3. So if good job in standard out output, basically. And then the reverse is whether or not we should stop searching. So if try again in standard out output, then we want to stop searching. I think that's all we need. And like, we shouldn't need to look at the binary at all to be able to get this correct, because we know what the outward behavior of the program is just from having run it. I guess we didn't actually run it, but now we can see, okay, it prints try again. And it actually prints it with a lowercase a, yeah. Like that. And put the period on there as well, why not? Okay, so do I need to, okay, I either did that without thinking about it, or they already had the argv1 in there. And of course I need to fix the print statements. Okay, so it went ahead and searched through everything and was able to find a condition where we printed out good job. Nope, because I gave it to the wrong program. Okay, that's the password for the angr find condition thing. Now, if we look at this in radar, I am curious what the main function looks like. Ooh, it's apparently a very big graph. What the heck? Why is it so big? What is going on? This is not helpful. Okay. There's a lot of stuff in here. Okay. So I guess the approach that they are taking to make it difficult to know how to get it to print good job is that there are many, many locations where it might be printing good job. And if we wanted to go the instruction route, we would need to put the address of each of the blocks where it says puts good job. We need to put all of those into our list of find addresses, and that gets, maybe untenable or at least tedious. And so instead we just say comprehensively, if the program ever prints out a good job, then we met whatever the condition was that we needed. And in fact, we could then look at the state and review the basic blocks that it had gone through and find the exact code path that actually worked. But yeah, this is a pretty ginormous function in terms of the actual graph that it gives, and radar is not that great at showing. I mean, because it's a text program, like the zooming in and out is not very granular, or it's not very smooth. I don't know the right way to put it, but you can only minimize that graph or zoom out of that graph so much. So it's not very helpful to look at it in radar either. Okay. Let's try the fourth one. So this one is symbolic registers. Let's see what we've got in the comments. angr doesn't currently support reading multiple things with scanf. Okay. You'll have to tell the simulation engine to begin the program after scanf is called and manually inject the symbols into registers. Interesting. I wonder if that is still true, just because if this one is using, yeah, like this has been not updated in over 2 years, and most of this content, this stuff is like 3 years old. So it's entirely possible that the scanf logic works now, but we'll go through with the intended way of using this or going through this challenge. But I think it would be interesting to see if we can also avoid having to do whatever this stuff is about skipping past the scanf and manually inserting password stuff. So let's see. Sometimes you want to specify where the program should start. The variable start address will specify where the symbolic execution engine should begin. Note that we are using blank state, not entry state. So yeah, we get blank state, which, I mean, I guess that's what you have to do, but it's gonna have like, I don't know what is in memory at that point. Maybe it does have the loading stuff figured out where it's mapped in the binary segments at the right places and stuff. Certainly any memory that it would be written dynamically as the program goes, you'd have to force that in. And there's functions where you can say load this data into memory at this location. And you could then set up a situation as you'd like it. You could probably take a dump of an existing program and then use that as the basis for your memory state, and do something akin to a snapshot fuzzing, but sort of snapshot symbolic execution. I would assume that that stuff is probably already written as existing plugins or things that are part of the angr toolkit already. It just seems so obvious, but if not, I think that would be a nice project to add on. Just be able to like pull in a core dump taken from a debugger at some particular point in time and go from there. Okay, so we need to figure out a start address. So maybe we'll open it up in Radar, look for the address after scanf returns, and then we create a symbolic bit vector, which is the data type angr uses to inject symbolic values into the binary. Sure. First parameter is just a name, and then you would give it a size as well. Yeah. Okay. Okay, so we're basically going to create bit vectors that will represent the data that has been like parsed in with scanf. And then I guess we will set certain registers to have that data. Which is interesting. All right, let's look at it. So it's in the get user input function, I guess. It's my guess. Yeah, we call it scanf, and it's doing %x, %x, %x. Okay, so it's going to read in what, the hexadecimal number? I don't know if there's like that direct correlation between printf format specifiers and scanf. %x would be printing a hexadecimal number in with printf. Yeah. Okay. So, and if we have no length modifier, then it's going to be an unsigned int size. Okay. Okay. So I see. Right. Okay. So we are not defining what the value of these bit vectors are. They're symbolic bit vectors, which is why it's BVS. So that means that it's like could be one of multiple values, or could be several different values. Let's say, I guess 0 or more. But the main concept is that its potential values are defined by the constraints that are on it. I guess the core constraint is the size. So if you have a bit vector of size 1 and no other constraints, then you've got a 0 or a 1. You've only got two possibilities for what that bit could be. And then if you have another constraint because some bit of code checked whether or not it was 1, then if that check passed, the code path that follows that state constrains that value to be 1. And then if you have a bit vector that's of size 32, you could have 4 billion possible values in that bit vector. So you want to have a lot of constraints to minimize the number of possible values that bit vector symbol could have to reduce your search time, basically. Okay, so let's look at the binary, see what it is. It's a 32-bit ELF as well. So our integers are going to be 4 bytes. So we'll have 32 bits for the bit vector symbols. All right, so then we've got 3 of those, and those get scanned in and then get moved into first EAX, then EBX, and then EDX. So let's say right, EAX, I think that's the right order, because we're going to push these in opposite order. So this is the first one at 18, and then 14, and then 10. Okay, I think that's fine. And then we can put our start address at the NOP, basically. So what do I want to do with this? Get user input. This will be our start address. And we will have set up these registers in the initial state. And then we want to do the same kind of check. Good job in standard out output. And try again in standard out output is the abort case. Okay, so solve for the symbolic values. If there are multiple solutions, we only care about one, so we use eval, which returns any, but only one solution. Pass eval the bit vector you want to solve for. So this is, right, we weren't really worrying about any symbolic values in the previous examples. Technically, the standard in data was the symbolic values that got sort of turned into a concrete value as it solved by going through or as it got constrained by going through the simulation process. But at this point, we are going to find a state that has gone through and gotten to printing out good job, except we don't have, we have an explicit piece of symbolic data. So then we have to say, okay, given a state that got to good job, evaluate what are the possible values of the symbolic piece of data that we used as an input. And it will eventually find us one of those. There could be more than one, but with eval, we're only asking for one of them. So yeah, we will go ahead and eval all of those. Oh, this is one. Okay. And then we want to print out the solution. So I'm going to do we'll print everything out that way. Okay. So that'll print out what we should have typed in order to get the state that we need, I guess. So if we do like A, B, C, that's not right. But if we interesting, we've got a syntax issue, line 78. Oh, need another prime. Okay. Could not find the solution. Cool. So exit state is over. 256 possible. So, no, we put the start address. So the start address is that NOP, but we don't necessarily know where we would be returning to, I guess. So let's not go. Okay. Let's see. Did we do anything with? No. Okay. So this function has been carefully constructed, I think, to allow us to set these EAX, EBX, EDX and sort of jump into the code at the location that we would return back to. Because I think the problem of starting at the NOP is that when we get to ret, we don't actually have a stack set up properly, so ret doesn't know where to return to. So we want to just pop into this spot. So we go to main, and we want to pop into here. See if that works for us. Okay, so it found 3 values that I guess we could type in to get good job to print. Do we provide it without the 0x? No, still not correct. Interesting. So what am I missing? I guess I'm going to use GDB to see how scanf works with it. And we want to go to the NOP, I guess. Let's try it without the 0x's. So then in EAX, we've got that value, and EBX and D, like those are the values that we had put in that it seemed to think would result in good job being printed. So I guess we need to investigate further. Let's see, and we've still got those in the right registers as we go through everything. I want to so what do we see? What are we putting into ECX? What's in 14H? Well, let's just... So, not equal is not taken. Okay. Then we do the next compare. That's also not taken. Do the next compare. It's not taken. So we're going to this puts at D7. Oh. So the last one is failing. So messed something up in the code, maybe. Yeah, that needs to be EDX. Okay. It makes sense that there wouldn't have been 0. Then let's see if this works. Now it prints. Good job. Okay, so yeah, that's a good introduction to the idea that we might need to provide explicit memory addresses or register values that are symbolic. And then when we get to the success state, we can evaluate those symbols to, or symbolic values rather, to see if they, which concrete values they actually have. If they have none, then they're unsatisfiable, which usually means we wouldn't even get to the success state, because I think the execution engine or the simulation manager does not keep trying to progress those. Yeah. Let's see. I guess we could try. I'm going to try an alternative approach to this one where we do entry state and we don't set any of this stuff. So this is similar to what we did on the previous challenge. And print solution state.postx.dumps. I think something like that. What would be your advice to be totally anonymous on the internet? First off, hello, Katarina God. To be totally anonymous. I mean, I think that's probably my first piece of advice is to probably not think about the task in that term. Think about it more in terms of who, generally speaking, in a security mindset, you want to think about who your adversaries are and what their capabilities are, and then you can assess how you want to protect yourselves against those particular capabilities. So if you want to be anonymous from a particular person, then there's a lot more specific advice that could be given based on, somebody's knowledge of that person and their capabilities of seeing who is, I don't know, if it's some random person at your school, let's say, and you want to make sure that they don't know that it's you that's posting a negative comment on their Instagram, for example, that's a very different challenge from if there's a person who happens to work for the NSA and has access to their tools and is willing to use them for their own personal vendetta against you or something, right? And you've pissed them off for some reason and they want to listen in on all of your conversations through social media and stuff and use that to mess with your friendships, or I don't know, just stalk you or something, like, which are, apparently are real things that some people that have worked for the NSA have done. Um, Maybe not people they pissed off, but maybe like women they wanted to harass or something. Um, so those are very different concerns, and the work that you need to do is going to be very different in both of those cases, I guess. So talking about like totally anonymous is maybe is too broad of a remit, because I think um, it's you're never gonna get to that bar of being completely totally anonymous, I would guess. Certainly, if that's possible, I'm not somebody that knows how to do that. So if it's like you want to be anonymous from the US government and all of their spying capabilities, um, I mean, that's a hard one, honestly. A lot of people would say, like, hey, use Tor and then you'll be anonymous, but Tor is also has been funded since the beginning by the CIA and is pretty much known that it was used as a designed as a tool that the CIA agents could use to be anonymous and connecting back to their handlers in the US or whatever when they're out in the field. Like, I don't think it's necessarily an obvious solution if you then want to be anonymous from the government that created it effectively. And a lot of people don't want to look at Tor and be like, oh, it's tied to the government. They consider that like um, a heinous accusation or something, but it does seem to be true, regardless of how much they wish it wasn't. Uh, so, but if the U.S. government is not the people that you are looking to hide from, which I think is the case for a lot of people that want to do something anonymously on the internet, Tor is probably a good option. You get Tor browser. A lot of people put a lot of time into trying to make that anonymous and secure, and so I mean that's an easy recommendation, but again, it's like doesn't necessarily cut it for every use case. And there are definitely ways of using those tools that are make you more or less anonymous. Like you could use them poorly. Certainly, if you use Tor and then you write a message that says, "Hey, my name is such and such. I live at this address," then you're not helping yourself anonymity wise, I guess, right? And that's a very trivial example, but there could be other things that you do if you log into Tor or you use the Tor browser and then you go log into your Facebook. Then you're not anonymous. You've just connected into a thing that is connected to your identity. Stuff like that. Granted, it might protect some other website that you go to from knowing that you are also connected to Facebook, but Facebook will know that you're logged in, even if you're doing it through Tor. So, yeah, I guess if you're running something like Silk Road and you're doing drug trafficking or whatever else was going on there, and you attract the attention of the federal government of the United States, I mean, it's not like they necessarily broke Tor to do that. I think they used their normal techniques of like law enforcement and finding somebody who probably didn't practice good enough what they call like operation security, OPSEC. So the stuff that they said, right? Yeah. So they used Tor, but at some point they must have mentioned something that could have been that was able to be related back to them, and then somebody who's really paying attention can find that, and if they have the investigative capabilities of the FBI or whatever, they'll be able to track that lead down and find you or find somebody that knows you, and then they can lean on that person to reveal who you are, etc. Like, these are age old, or at least decades old approaches from law enforcement. um, so I don't know, I certainly don't have any advice on how to anonymously go on the internet and break the law. I don't know how to do that. But I think if you look up like privacy concerns, there's like Um, I don't remember. There was a nice website that had a lot of like good suggestions, but I don't remember the name of it anymore. And it was just sort of like things that you could put into your browser or maybe use Tor or whatever. Very like general purpose suggestions. I would say just in general, I'm not the kind of person to be able to answer that. Unfortunately, that's not like what I've invested a lot of my time into. Maybe Reddit would be a good option, or if you want to talk to somebody on Twitch, the kind of person that I have that I would think might know is oh, what is his name? Let me find this guy because he's pretty awesome. Even if you uh just want to watch his channel. Whoops. Whoop. Just start playing stuff. Thanks. Where is it? I follow too many people on Twitch. I can't find people when I want to. Hmm. Dowright. I'll throw the link into chat as well. I so the art of invisibility from Mitnick. I mean, certainly stuff can change year to year. 2017, not too long ago, to the point where I would say don't bother with anything written from then or earlier. But more, I would say, like I don't know that I am interested in the opinions of Kevin Mitnick. Basically, I think he falls pretty squarely in the category of somebody who is more interested in their public mainstream reputation than being really good at what they're doing. So, you know, it's entirely possible that the stuff in there is perfectly fine. It's just like he's not the resource that I would think to go to. So I linked this guy Dowright. I don't know if he has a lot of info around being anonymous on the internet. What I've seen him work on a lot is network security related stuff and like firewalls and stuff. And obviously that's not exactly the same thing, but it feels like it's closer to the viewpoint of like, hey, if you want to understand how you could be tracked on the internet, it there are elements of understanding what network traffic is actually going on, but there's also you know levels of like you are being made less anonymous by the programs that you're using, and the network traffic they send is not necessarily something you want to block because you don't want to block all of that traffic. You just want them to not send certain pieces of information that are like provide a signature of who you are, and that may be very difficult. And the solution might be to not use those programs at all. But in general, it would be my guess that he might have better insights into how to be anonymous um, than I would. I don't know. Again, it's not the kind of thing that I've put a lot of my time into learning about. I like use a VPN, but that's like minimal level, and I'm sure that uh, using certain programs through a VPN still makes you not very anonymous. Um, One thing I remember reading or hearing about is like if you have just using the browser that you have and all the specific versions of plugins or associated pieces of software connected to your browser can be a really good signature all on its own, even if you've turned off any explicit sort of tracking cookie kind of stuff. So, you could go a long route towards like trying to filter what headers are being sent when you visit a website. When you do HTTP requests, you could take off headers that might be more indicative or modify them to be more generic, stuff of that nature. But again, that's like outside of the scope of what I know how to do, or at least have attempted to do. And this might be a category where like a little bit is better than nothing. So if you aren't using a VPN, look for a VPN that is more useful for being anonymous, I guess. So if I set up a VPN that's like my own personal VPN, and I'm just using it because I need to be able to access things from an IP address that looks like it's in this country or something, that's not anonymous at all because I'm the only one using it. But if you're connecting to some VPN that is like, that IP is shared by thousands and thousands of people, and they have some policy of not keeping logs and stuff, then you get a lot more anonymity just from that layer. And if you aren't going that route yet, that might be the first step to take. Of course, Tor is, just like its own sort of nested sequence of VPNs. So if you want to just go straight to Tor, like that's also probably a good option. But again, entirely depends on what your what your adversary analysis is or something. I don't know. Hope that helps, and good luck with your desire of anonymity. Okay, so an interesting thing. So I made this alternative version of the solution for number 3 or 03, I guess. And this alternative does none of the symbolic register work that we were required to do in the like official solution, because I guess they fixed the issue with scanf and not supporting multiple items being scanned in, multiple distinct entries or values being scanned in. And since that was fixed, we can just start at the beginning of the program, run it until it says good job, and then print out what the input had to have been. And it turns out that works perfectly fine, and it gives us the exact same input as what we discovered through the other method. So that's pretty great, and it doesn't take a long time, even though this is a much longer string than some of the earlier challenges were. And Katerina God, thanks for the follow. Feel free to stick around. I'm just going to be working on this sort of binary exploitation stuff. If you're interested in maybe more web related stuff, over the weekend I'm going to do some try hack me boxes, or rooms I guess they call them, and those will probably be more in the category of web security, and maybe that'll be more relevant to your interests. I'm not sure what your interests are outside of maybe the anonymity stuff. Nmap stuff. Yeah, we definitely can end up doing Nmap for sure. I've used it before, and I know how it works, but I'm not like, I watch like optional CTF on here and John Hammond and stuff, and they're like doing try hack me and just typing in nmap commands from memory. Like they know, oh, this set of flags is exactly what I need. Like I don't have that level of familiarity with it, so hopefully I will gain some just by doing those rooms. All right, so 04. What was this one called? Symbolic stack. Okay. So This challenge will be more challenging than the previous challenges. It's a very challenging challenge. Since the goal of the CTF is to teach symbolic execution and not how to construct stack frames, these comments will work you through understanding what is on the stack. Okay, so there's going to be more explanation of how the stack works, which I'm probably not going to read through. Apologies if that makes it harder to follow, but my focus right now is what can I learn from angr, and using angr, and not necessarily reviewing the mechanics of x86. Okay, the addresses might not be right. It's fine. So they want to begin after the call to scanf, which is in the middle of the function. Oh, so this is probably effectively the same situation that we had in the previous challenge, except in the previous one, which I still have open in Radar, we called scanf inside of get user input. And if you recall, I was initially like, well, let's just start running our analysis from this NOP. But you're going to get to the return, and the return isn't going to be able to do what it needs to do. Like, it needs to pop a value from whatever ESP points to, and that's going to be the address it returns to. But if we haven't set up the stack, if we haven't put anything at ESP, and ESP is going to be modified by the leave instruction anyways, so if we haven't actually pushed EBP and the call instruction that had pushed the return address just prior, if we haven't done those things, then these two instructions aren't going to work properly. And we were able to avoid that by simply saying, okay, never mind, we will start the program here instead, because conveniently the three registers we cared about remain the same values even after we return. A lot of functions, if they set EAX, like if they overwrite one of these registers, they will generate code for that function that first saves the old value and then returns the old value before the call finishes. So these, in most cases, these registers would no longer be the right values, except for EAX, which is the return register. But EBX, EDX would probably be back to whatever they had before we called get user input. However, this function is basically, I don't know how they did it, but it works out specially to not do that. And so we were able to take advantage of just starting the program here. My guess from what they're saying here is that if we were to look at the next program, it doesn't call a separate function to do scanf. It does it right, like maybe it calls scanf right here, and then we have to do a bunch of stuff, and then maybe return, like, basically we don't have the ability to avoid generating a stack that works properly. And thus we need to define what the stack looks like when we start our simulation. Yeah. And really, we're probably going to fake a very small portion of what the real stack would be, because we, how to say it, if we were starting at a very nested function call, like if our call stack had 10 functions in it. So we were nested 10 functions deep, and we needed to run the simulation long enough to get all the way back up to the first function, main or whatever, underscore start. We would have to actually be able to simulate the stack for all of those stack frames. But most likely, in this very contrived example, we won't have to simulate too much of the stack. Maybe just the one stack frame that we're in. And that'll make things simpler, because then we don't have to generate a bunch of data to represent the full stack. And I mean, it just feels like if we made all of that symbolic, then we've got just even more symbolic data than we really want to deal with, because I think most of those values on the stack aren't going to be relevant to getting the execution path that we need. There'll be things like addresses of functions to return to, and the old values of EBP and stuff. So, okay. Hopefully we won't have to put too much on the stack. And again, because this is dealing with scanf, I think we could probably do the simpler solution as well. I'll try that afterwards. Do we start on the instruction immediately following scanf, or the instruction following that? So what do we start on the add or the thing after the add? Yeah, so this add is cleaning up the stack after the call. Basically, we pushed 3 things onto the stack, and then we are adding 4 values worth back to the stack. Although we also subtracted 4. So I don't know why we subtracted 4 from the stack pointer right here, but the net impact of this set of instructions is the stack pointer has gone down by 16 bytes, or just the address is 16 less than it was at the beginning of this chunk of instructions. So then after the call, we add 16 back to it so that it resets the stack pointer to what it had been. So we're cleaning up all of the behavior related to our call to scanf. And that's a pretty common thing. I mean, it's just how the compiler generates those results. So we're adding to the stack pointer right here, adding 16 to it there, adding 16 to it here. And as you can see, like, we subtract 12, then we push another thing which subtracts another 4 as the push happens. So then we reset ESP back by doing add 10. Now this is just based on the calling convention that is used for these functions and the fact that we are in 32-bit, whereas I think the calling convention in 64-bit does not have the caller clean up the stack. Could be wrong, but I don't remember seeing a bunch of add ESP instructions every time we call a function when I'm reversing 64-bit x86 binaries. At the same time, you know, maybe I'm just like glossing over it in my mind because I know this is like not critical to understanding the function's actual behavior when reversing it. But it is still critical to the function, like to the code working properly, which is why we need to consider it when we're doing this simulation. So in their question, do we want to start here or start after there? And I would say we should just start after there, because if it's just cleaning up the stack pointer by moving it back to, you know, effectively take these 3 values in whatever was added to the stack by the sub instruction, taking those off of the stack, then we have a cleaner stack to work with for going forward with scanf. and then we just have to deal with what might have already been on the stack prior. Yeah, so since we're not actually calling scanf, we'll start after the add. Okay, well, let's go ahead and analyze it with radar. Okay, so then we are doing it in this function called handle user. But the key is that the scanf can't be fully separated from the calls to function and stuff. So what do we have on the stack before this? Nothing. So we've got, well, not nothing. We've got the stack frame sort of prologue, if you want to call it that, or the core stuff that is going to be in a stack frame that represents the frame itself and allows you to return from this function. So we've pushed the old value of EBP, so that'll be there. And at ESP plus 18 hex. And then just above that, at ESP plus 1C hex is, or I guess this is at 1C hex, and then at 20 hex is going to be the return value. And then we've got 18 bytes of nothing. At least by the time scanf does its thing, there is nothing there. Oh, that's not true. Sorry. Because these values are in there. So we will have. Yeah, what do we have? 18. If we are. I don't like. There is some chunk of this data which doesn't get used, I guess. Because we've only got EBP minus 10 and EBP minus C. So, like, EBP minus 4 and 8 aren't used. And minus 14 is also not used. I don't know. Okay, so we can start the instruction here. And then we know that we need okay, so we don't even have to worry about EBP, the old value of EBP, and the return address, because we can determine the success of our function, or our input rather, just without having to return and have the return work. So if we get to good job, then we're done. We don't have to worry about the rest of the simulation. Or if we get to try again, then we're done with a failure, and we don't have to worry about the rest of simulation. So really, we just need space for these two variables on the stack. Okay, so our start address is going to be, what the hell? Okay, that's what I wanted. Handle user. Start address is going to be this move instruction. And okay, I guess we can initialize EBP to whatever ESP is. This feels weird because I don't even know what ESP would look like at this point, but I guess that's fine. Do we want to subtract from ESP? Do we do that down here? Okay. We need to figure out what the stack looks like, at least well enough to inject our symbols where we want them. In order to do that, let's figure out what the parameters of scanf are. So okay. So I think, all right, we've got 2 parts to the password, and we're doing %u. It's going to be 32 bits. Pretty sure. Yeah. Unsigned decimal integer. Okay. Then, yeah, we've got our, is it not %u, %u? It is. I don't know why they have ... here. Oh, I see. They want us to figure out, basically, yeah, how big is password 0. Okay. So if password 0 is at EBP minus C, then it's going to end at EBP minus 8. So we've got 8 bytes of padding before our first stack variable, and then another 4 for the second stack variable, and yeah, those are the like EBP minus 4 and EBP minus 8 that we don't actually have. So should be padding length of 8. We'll subtract that from ESP, and then we're going to push, let's see, push the variables to the stack, make sure they push them in the right order. So EBP minus C is the first one. So that's going to be password 0, password 1. Pretty sure. So ESP gets subtracted by 8, and then we push password 0, which is going to be now at ESP minus C, and then we push password 1, which will be at ESP minus 10 hex. Okay, and then we can fill these in. And do we need, no, we don't need it as hex. Okay, I think that should be enough. Really, the complication is wrapping your head around how the stack works, and there's still a fair chance that I have messed this up, because I wouldn't consider myself an expert in it. State.sc is deprecated. Use state.solver. Okay. Oops. Let's see if that's the right input. It was. Okay, so I got it right. Yeah. Basically, we constructed not even the entire stack frame for this function, but just enough to be able to have symbolic variables at the right location in memory where stuff is going to be read in, where the rest of the function code expects the scanf results to have been stored. And then we can just work out, well, what was the value that needed to have been stored there for the rest of the function to work? And that's good enough. Cool. You know what? Let's see if we can get this to work again still. Even without modification, I would think it should work. Yep. So, in the meantime, angr has, in the last 3 years, angr has been updated to include enough functionality that we don't have to do any of the work that was part of these challenges. We can just use the same approach that we used on the challenge 02 and just say, hey, run the program until run every possible version of the program until you get to good job, and then tell us what was the input needed. So, excellent. Really appreciating angr for these challenges. We'll see how it stacks up when we get to the non-introductory challenges, I guess. On to 05. And this one is symbolic memory. Similar to the stack, because stack is memory. But, presumably this is talking about heap memory or something. Okay, we're doing scanf again. We're scanning in 4 different 8-character strings. Or at least maybe up to 8 characters. I don't know. And okay, it writes to a global variable. So actually not even on the heap, just in the data segment. BSS maybe. Okay, and basically what we're doing is we're generating some symbolic bit vectors, and we're going to store those into memory, and those will later be read by the remainder of the code. So I guess we again want to start after the scanf call. Yeah. So we'll start at the move instruction. And we get fancy with it. Want to, yeah, we can do it that way. And this is not even how you would write it in modern angr, because we could call something like .solver.bbs, I think, but I'll keep with how they have it right now. But it might be a good project to go through and update these to match the current documentation. So what are the, oh, they're 8 bytes, so 64 bits for each of those. And okay, then the addresses that we are storing stuff at is, let's see, what the heck? Weird. That's not print an address. So no dot. Yeah, there it is. Why didn't it find it? Oh, maybe because I put a space on there. Okay, so just do it this way. And so we're at A1, BA1, C0. So that's our start address. It's the lowest address. And then for the in password, okay, so because we're doing 4 different things, and there's just 4, not 8. I am creating these in an array. Let me double check something. For the in password. It's called SV for symbolic value. We can do it as a just pure string. See if this works. It's taking too long, I guess. It's not a valid cast tag. Okay, so we can only do cast to bytes and int. So real quick. Okay. So plus equals does work in that case. Decode. Yeah. Let's see how this goes. All right. Oh yeah. That's what I want to do. Need to put the spaces in there. Okay, awesome. So in theory, this will be our input. Good job. Oh, didn't get the N. Okay. Yeah, cool. So, you know, kind of the same as the stack one, except instead of pushing addresses that are on the stack by pushing something relative to EBP or ESP, we are pushing absolute addresses of somewhere in presumably the data segment. One of the you know, maybe the BSS section or something. Okay. Let's move on to the next one. Symbolic dynamic memory. Nice. So we're just sort of going through all the ways in which a program can use some piece of data and represent it as a symbolic value so that we can then evaluate it once we've found a state that got to the good state. So I'm certainly happy to go through. And you know what? Let's I want to try the alternative as well. Or sorry. see if, because it took, a noticeable amount of time to run through this one. And I'm curious if it takes even longer to go with the alternative method. No, basically took the same amount of time, I'd say. So, and still able to use that one solution. So that's neat. And I bet it would work on this one as well, because these are all just variants on the scanf thing. Okay, we'll figure out the start address. It takes 2 strings. With just 2, I'm just gonna do it all manual like they want. 64 bits in an 8-byte string. That's what they tell me, at least. My guess is that these complex function implementations are doing the limit the input values to uppercase letters in order to cut down on the time that, I mean, maybe it has to do with the algorithm itself as well, but certainly it shortens the amount of time that angr needs to take to search through possible solutions, because we've cut out a lot of, each individual character, each byte within our bit vectors can only have such and such value. So that is helpful. Okay, let's see. Okay, so because this version of the scanf challenge is going to malloc dynamically allocate some memory to store the scanf input values. Right, we're pushing EDX and EAX, and those are the addresses of buffer 1, buffer 0. Or sorry, we're getting whatever value is coming out of this fixed location, I guess. And that's where we're storing the address that comes back from malloc. So, okay. That seems fine. Where are we? Yeah. Okay. And so we are going to, again, start down here and have created memory somewhere that is usable. So I might need to look at the virtual memory of the binary. Probably something that the loader can tell us about. Is how we would want to do it in a more realistic scenario. Because really we need it to be a memory address that is acceptable in the simulation, not necessarily in the reality of when we run the program. Okay, so this will be our start address. And we'll create our two things, our two elements to the password. And our fake addresses will be well, let's deal with those in a second. Why do we have 1, 2, 3, 4? I don't understand where buffer 2 and 3 get referenced. Okay, so buffer 0 there. That's weird. They're like sorted in this way. Actually, and then it's AC. So let's see, what do we have at okay. The end of BSS is at B0. And we need where is this BSS start? Okay. So quite a wait, what? So I guess they have a huge BSX section for us to just put stuff into in this one. I don't. Yeah. Okay. So if we put stuff at 804B000 and whatever. Doesn't particularly matter because we're only scanning in 8 bytes, but I will make them significantly further away. And then at those addresses, we will store our symbolic bit vectors. Yep. Then we'll run it. Good job, state. And all right. I think that can work. Let's find out. Claims it worked. Yeah. Cool. Now let's try the alternative. Also works. Yep. Happens to do some additional stuff in the string compare, I guess. But generally speaking, that solution goes the distance. All right. See if there's another one in this scanf series, or if we are switching to something else. Symbolic file, probably the same kind of thing. Maybe an F scanf, is that the thing? Yeah, we can scan from a file descriptor or I guess a file pointer. And okay, so we can solve this in multiple ways. For the sake of learning how to simulate an alternate file system, please solve this challenge according to structure provided below. As a challenge, once you have an initial solution, try solving this in an alternative way. So certainly I'm going to try throwing that script that's worked for all the past 5 or whatever at this one as well. Loads the password from a file using the fread function. Okay, so it doesn't do scanf. Or fscanf, rather. If the password is correct, it prints good job. In order to keep consistency with the other challenges, the input from the console is written to a file in the ignore me function. Okay. I'm not sure what they mean when they say to keep consistency, it prints the input from the console is written to a file. Okay. So we want to know where fread is reading from. and then we can simulate a fake file system with that file. And we can represent that file as a symbolic value. Okay. So, not sure why we aren't just doing entry point on this one. Because the reason that I thought we were skipping beyond the beginning of the main function in those previous challenges was the use of scanf, whereas we aren't using scanf here, so I don't know. Or maybe we are using scanf, but not in a way that has been mentioned. Let's look at it. Yeah, I don't see. We do have them, but they are not used. I don't think. Oh, maybe. Oh no, it does. Yeah, it is using scanf. Scanning in 64 byte string into a stack buffer. No, into a buffer, static buffer. Oh, that's what they mean by consistency. So to keep it consistent with the fact that we are taking input and using scanf to read that in, but we don't care about the data in that. How to put it? We don't care about the data that has been input. So, okay. We can honestly skip past probably scanf, ignore me, and memset. And then, so let's do that. So throw it on the sub. It's also kind of annoying. No, that should be fine. Okay. Let's see if that'll work. Okay, so then the file name is ojksqydp.txt. Yep. And the size is going to be 64 bytes, I guess, because that's how much we're going to read in. So then we have symbolic memory. So we create a new chunk of symbolic memory, I guess. Okay. Construct a bit vector for the password and then store it in the file's backing memory. I see. The store method works exactly the same as the store method you have already used. In fact, it's the exact same method. That means that memory.store address bit vector will write bit vector to the address we specify in this memory. Unlike our program's memory, we want to write to the beginning, as the Linux file will stream data from the beginning of the file. Yeah, okay, so we're going to use address 0 because there's no like fseek or anything, so we're reading from the first byte of the file, which is equivalent to address 0 in the memory space interpretation or conception of that file. Right, I think it's going to read 64 bytes from the file that is just f opened, and it's going to read those into the buffer. Then it'll close and unlink the file. It'll do stuff with the buffer, and then compare the first 8 bytes of the buffer. So really, the file could be, well, we'll make it 64 bytes, but it's only using the first 8 bytes, it seems like, for doing the password check. Okay, but it's using the first part. So, oops, should be 0, I think. All right, and then we create the file using the file name that we set. File options. Where were those defined? Oh, down here for read. Okay. Content we need to supply is presumably the file backing memory. Is that accurate? Yeah. Okay. So we can set symbolic file backing memory. Not gonna fix it because because Python. Okay, and then we actually need to design a file system, which is just a dictionary mapping file names to these sim file objects. That's cool. And then okay, and then we read the password, which is it's technically the entire file, but presumably it'll be a null byte after the first 8. I think this is enough. I think I've filled in everything. See if it works. No. Got multiple values for argument content. I don't, what? How is that multiple values? It's just the one value. This is a scalar value. Pretty sure. Yep. It's not like type. Maybe they changed the parameters. Where are the reference docs, anyways? Were they in API docs? Sim file. Waiting on search. Is it ever gonna complete? Generally doesn't take this long. Why don't we just work through part of Sim OS maybe? Storage? Yeah, sim file. No, sim file. Dot sim file. Okay, sim file base and sim file. So it does not take the, let's see, so has and writable, and concrete. Okay. Doesn't take file options anymore. We can just pass this as the second parameter, I'm pretty sure. And it's assumed to be readable, and we could set things to say it's writable as well, but we don't have to worry about that in this challenge. Can't handle content of symbolic memory type. Okay. Even though that's the whole point, huh? So I think I can simply, I think they've switched it around, and now you can provide the bit vector directly, and it will like initialize the backing memory. So we can simply provide password as the content. You don't have to store it either. Okay, seem to be okay with that. It doesn't have a deoct. Fine. didn't find anything. Found it works with a null file, or it's not. I can't decode it. See if that helps at all. Okay, I see. But it is all null bytes. I don't think that's the solution. So OJK SQYDP.txt. But it did print out good job. When we had a buffer of no, like all 0 bytes, I feel like that is incorrect. Um, I mean, it's not going to be any different, I'm pretty sure. Do I need to do this as a bytes? No. OJK SQYDP. Maybe they've changed around the file system stuff. Let's give that a shot. Sim file system is not a thing. lowercase s. Doesn't have sim file system either. Oh, it's in a completely different module. Okay. State plugins dot file system. Still getting that issue. Okay. See, now if we exit there, right? So it's trying to open this file and saying it's unknown, even though we have put it into the file system. Oops. Can we eval something like password file.content? There's no attribute content, huh? Guess we could say concretize. Let's just do it with all the bytes. There's no attribute solver. What's the state? Should we give it set state? Okay. Maybe that's what we were missing earlier. Should we do it down here, I guess? Still not a... Unless that is the successful thing. Just feels wrong. It feels like there should obviously be a value in there. But we can go ahead and rather than print it, we can say just output that data to a file. Right, all zeros for 64 bytes. Yeah, does not work. So I mean, maybe if we connect it at the beginning. Still nothing. Yeah, we need to figure out how we're supposed to use okay, let's, instead of setting the initial content to be our bit vector symbolic bit vector, we will set we'll do a store oh no, we don't need the length. And now solution is going to be let's see if it works this way then. ports inspect and store. This is in angr storage memory 482. Self.state. So also doesn't work. Yeah, I don't know how I'm supposed to use simfile. Let's look at the normal docs then. The emulated file system. Let's say instead of doing it this way, say postfix.fs dot. How do they list it down here with insert? What? I guess that's the issue. Yeah, that'll do it, I guess. So we were always getting this warning that was confusing to me. I wasn't sure if that was, the core of our problem or related or not. I mean, obviously related, but not sure if it was what was actually preventing things from working. And I feel like it's probably working now. I haven't checked yet. But it was saying it was opening an unknown file. The program was attempting to open an unknown file, and we should have set this file in the file system, but that apparently wasn't working. Now it has worked. Okay, so we run it. Still nothing? Why doesn't it find the file properly? I guess I can try entering this text as the input as well. Yeah. Where does it do the thing? Oh, I see. So we can remove this file. Oh, I didn't want to remove that one. I'm gonna remove. Where was oh, I guess it deleted the file for us. Okay. So if we run it and then put in the password, it does work. And it creates that file and then deletes it later. I guess that's what the unlink is. Okay. So the whole issue was you now say state.fs instead of state.post6.fs and insert the file through that mechanism. That's okay, fine. Yeah, well, I think that's all that I'm going to get to today with this series. We still have how many more? We'll have constraints, hooks, sim procedures, sim scanf, vera testing, and then some other ones. So maybe we can get to a few of these. I do feel like the fact that it's been a couple years, the more involved stuff that we do, the more likely it is that the code has changed. The API for angr has changed, and so we may have to spend more and more time going into the docs and figuring out how to write the equivalent for these. But the challenges should still be solvable. I guess I can try that alt one. Let's see. This is, I don't know. I guess technically it should work because we had to put it into the way the program actually works is it takes your input, writes it to that file, and then reads it from that file again, basically. So this mechanism, the alt script that I have is only going to print out what needed to be typed in standard in. But since technically the way the program works is you do have to type in the password in standard in, and then it will save it and check it through reading the file, it should still work. Yeah. And it did, like, for whatever reason, guess some random non-null bytes for the remainder of the input that you can provide, but the main thing is that the password comes in the first 8 bytes. And I guess that's because we scan in 64 bytes. Yeah. Okay. So good progress with angr. I feel like it's a pretty powerful tool, and this CTF, as they term it, is nice as a tour of the different ways that you can use angr's tools to apply different techniques. The challenges are, you know, I wouldn't even really call them CTF challenges. They are more like uh, textbook, like end of chapter exercises. Which, granted, CTF challenge is sort of akin to that in some ways, but really it's in like I'm not having to look at these binaries and try to figure out what are the things I need to apply angr uh, to solve them. I am I know the exit condition that I'm looking for. I know that I'm basically looking for what gets sent on standard in, and I'm just seeing different techniques. It's definitely good training, right? But I think I will be happy to get into some of these challenges where I can see if I can apply them in a less uh, standardized scenario. But I might have to go, if those prove to be too challenging, I might have to go to these examples, of which they have several, and these are real CTF challenges. Um, and yeah, maybe these will be a simpler kind of challenge to work on. But what was making me think, hey, you can use it for maybe exploitation assistance. I know it can do ROP chain stuff. If I remember, I saw that somewhere. But vulnerability discovery makes the most sense of just finding the bugs that you can then exploit. I don't know if I'll do anything with CGC, which is like Cyber Grand Challenge. Apparently, they have a whole different binary format for that and stuff. So, um, in any case, I'll come back to this on Monday, and yeah, we'll just try to get good at angr, I guess. Keep getting, as they say, get good. But over the weekend, we'll be doing Try Hack Me, so we'll take a break from all the binary focus and work on probably some web stuff, some more general networking stuff. Nmap was mentioned earlier in the chat. Definitely probably do some stuff with Nmap, find out what network services are running, look through what is it, VulnDB or whatever it's called, ExploitDB, I guess. See if we can, or just maybe search it inside of Metasploit. I don't know. I don't have anything set up right now actually for doing that kind of work, so I guess I'll have to get those things installed. I don't have Kali or anything. I probably won't set up Kali. It's not really my preference. Yeah. So thanks for watching the stream, and I'll be back tomorrow.